This fifth lecture on linear harmonic oscillator, we shall first try to establish that the 0 point energy is just a manifestation of the uncertainty principle. So the minimum energy of the oscillator is E0. The energy, actually the energy of the oscillator is P square by twice m plus half m omega square x square. If we assume the energy in terms of expectation value, then it is p square expectation value by twice m plus half m omega square x square operator expectation value. Now we know that the delta p square, the errors, the standard deviation, if the standard deviation in the measurement of p is delta p, then this is governed by since this is 0 for the harmonic oscillator, so it is p square. So we can replace this by delta p square, so we write it, this is p square expectation value by twice m plus half, similarly half m omega square x square operator expectation value, and this can be written as delta p square by twice m plus half m omega square delta x square. This is the energy expression, and we have established in the last class that delta x n delta p n is equal to n plus half h cross omega. So the minimum uncertainty product is delta x delta p is equal to h cross omega by 2. So this is simply h cross, and so it is h cross by 2. So we write delta x is equal to delta h by delta p by h cross by 2 times delta p. So we replace this to get the energy expression like this, delta p square by twice m plus half m omega square, and for x square we write h line square by twice delta p whole square. So on simplification, this becomes delta p square by twice m plus this is 8 h line square m omega square by 8 delta p square. This is the energy. We want to make it a minimum one, so for minimum, for E0 to be minimum, we must have is equal to 0. So first term is delta p by m, and second term is so this gives you delta p rather delta p square is equal to so the E0, the corresponding value E0 at delta p is equal to m h lines omega by 2 is equal to p square by twice m, so this is m h line omega by 2 from this, and for this part we will have h line square m omega square upon 8, and for delta p we this is the expression for p square. Then there were 2m, sorry, this is 4m, because this is p square value is this, and when we divide it by this, and then we have used this, and for delta p is equal to 2 m h cross omega. So the first term is m cancels out, 1/4 h cross omega. The second term has also the same contribution, so this is half h cross omega. So we see that the h cross the 0 point energy is actually in accordance with the uncertainty principle. Another one thing I have forgotten to say, that the correspondence of quantum oscillator with the classical oscillator. If we consider a classical oscillator in a state n, then it has its extremities at plus minus 2n. So, and if we have a quantum oscillator in a state n, then it will the wave function is the classical description is this, and as n increases, we see the quantum behavior is something like this. Sorry. So as n tends to infinity, as n is much greater than 1, PC, the classical prediction, and the quantum prediction tends to each other, becomes similar. So the correspondence principle here is that when n tends to infinity, the classical result is nothing but the average of quantum result. But for small n, there is drastic difference between classical and quantum result. As for n is equal to 0, quantum result shows that the particle is most probably to be at the equilibrium position, where classical prediction is that it has the minimum probability, and this discrepancy between classical and quantum result goes on decreasing as n increases. And now I come to the case of selection rule. This is the basic principle behind the spectroscopy. Now we consider a harmonic oscillator. Harmonic oscillator is which has a Hamiltonian P operator square by twice m. The kinetic energy operator is always same, plus its potential energy. So this is the harmonic potential. So far as the potential is strictly parabolic, the theory that we have developed so far is applicable, and we can solve the Schrödinger equation to get the stationary states. Even if we add a potential V prime, which is alpha x, then this can be incorporated within this, and we write V is equal to half m omega square. x minus say beta square, this term can be accommodated within this plus a constant term. Which is a constant potential, and we can neglect it. So far as we add a potential which is a linear function of position, the earlier description holds good. Only thing that there will be a shift of energy levels due to this factor. That's all. But if we add some potential which varies as x cube or say something, that is a3x cube or etc., then this cannot be accommodated into the theory. And due to this interaction, the exact bound state will, in a bound state, the particle remains there for, if we call the time period tau is infinity in a stationary state. And the characteristics of the stationary state that if unless some external disturbance is applied to the system, the system always lies in a particular state. This is the definition of stationary state, that is, it has infinite lifetime. But if you apply such potential, then the system is no more purely harmonic. It shifts a bit from the harmonic model. How much will shift? It depends on the strength or the expectation value of V prime. If we know that the expectation value of V prime is much less than the expectation value of energy, if so, then we can say that the system is still harmonic, and there will be a certain changes over the harmonic oscillator states. That is, the particle may make a transition from one state to another state. Let us consider an interaction like O, which when acts on a state n, if the expectation value of this operator is small enough, then still the system is a harmonic one, and the system may make a transition to another state m. The situation is that the system is originally in a state n. When some interaction is applied on the system, say the system makes a jumps from here to there or there. Since this expectation value is small, the energy levels are still the energy levels of the harmonic oscillator, more or less. So it makes a transition from one harmonic oscillator state to another harmonic oscillator state. Now the question is that is this allowed process? That is, the concept is that M operated by, what is this? It means that the operator, when operates on a particle which harmonic oscillator which is in a state n, then it takes you to another state m. If this is all again an harmonic oscillator state, then this expectation value will not be 0. So this matrix element will not be 0. This is not equal to 0 for allowed transition. And is equal to 0 for a forbidden transition. So whether a system can go from one state to another state can be determined from the matrix element of the interaction. Originally, before the development of quantum theory, the experimental physicist would examine the spectra of a system very minutely, and from there they come to the conclusion that what are the possible transitions. Say it is in a n is equal in a state, then it is found that it can go one step up or one step down. If so happens, they define delta n is equal to nf minus ni is equal to plus minus 1 as the selection rule. That is, n can change either by plus 1 or minus 1, and these are the only possible transitions. Now we come to the harmonic oscillator step. First I will say something about the interaction, and then I will go to the selection rule. The interaction, if we consider, it is in general is a function of xp. As per the Hamiltonian dynamics of classical mechanics, any dynamical variable related to a system can be written as a combination of x and p's. Say for example, this may be summation over ij c n I m j x n I p m j. As for example, the interaction may be proportional to x, it may be proportional to x square, it may be proportional to p, it may be proportional to p square, it may be proportional to xp. If this is the operator, we must antisymmetrize it, make it Hermitian, so we write it this, and the other things, of which this is a very important interaction. This is called optical transition, optical or dipole transition, dipole interaction, optical or dipole interaction. Let me explain. When some interaction, say an electric field is applied to an atomic system, then we see that if the field is applied in this direction, the nucleus shifts toward in the direction of the field, and the center of electron charge charge shifts in anti-parallel to the electric field, so that a net dipole is created. This dipole moment, if we call dipole moment, it is proportional to the separation. If we measure the distance from the nucleus, so it is the proportional to x. That is, it is called dipole transition. And for atomic system, it is the most important interaction, and as a result of this interaction, system makes a jumps from one state to another, and the corresponding photon which is emitted is found to lie in the optical in the visible range or in its neighborhood. That's why it is also called optical transition. So it is a very important element, interaction. Now we come to the selection rule. We have already heard that mxn, this is equal to 0 if m not equal to n plus minus 1. So the selection rule is delta n is equal to plus minus 1. If we consider this interaction, so the selection rule here is, so this n is the initial quantum number, and this is the final quantum number. So if the final quantum number is related to initial quantum number by this relation, then the transition is possible. So this is the selection rule. That means if we interact a harmonic oscillator by optical or dipole interaction, then it can go one step up or it can go one step down. This is the only allowed transition under dipole interaction. If the interaction is quadratic in X, then the system may stay over here, which is elastic, or make a transition from here to there, double excitation, or it may go there, double de-excitation. Similarly for P. For P, we know that the matrix element of P is this. We have already worked out all these things in the earlier class. So again the selection rule is same. This is delta n is equal to plus minus 1. Here delta n is equal to 0 plus minus 2. If we consider x cube interaction, for x cube interaction the selection rule would obviously be so the selection rule is delta n is equal to plus minus 1 or plus minus 3. From this information, if we have an X system which is interacting by some perturbation, which is being interacted by some perturbation, and we want to know the nature of the perturbation, this selection rule helps us to find the nature of the perturbation. Say the system is originally in the state n is equal to 10, and we see that the intense line is found with n is equal to 12. Intense lines means this line, the transition is very prominent. So that means that the selection rule that comes into play is plus minus 2. So in this case it is plus 2. So the interaction is most likely either of this form or this form. So we in the position basis, the interaction is most likely x squared. So we can infer something about the nature of the interaction from the study of the spectra, and the selection rule provides us a very handy tool for analyzing the spectra in for complicated system. One thing I want to make clear, that the selection rule depends mainly on two things. One is the nature of interaction. As we see that as the interaction, the form of the interaction changes, the selection rule changes. Secondly, it also depends on the system under consideration. Here, these selection rules are applicable for harmonic oscillator, and this will also be applicable for systems which can be converted into equivalent harmonic oscillator problems, as the vibrational spectra of the atomic molecule and many other things. This is the importance of selection rule, which will be prominent when you will study the spectroscopy, when we will study spectroscopy.